cutting through the noise and getting right to what matters. And today, well, we're diving into something truly captivating, an idea that's echoed for millennia: cosmic harmony. You know, the music of the spheres. Imagine the universe itself, like a grand symphony, celestial bodies moving in perfect mathematical order, composing silently. It's this beautiful vision, right? Famously from thinkers like Pythagoras.
It really is a profound thought, this idea that numbers, harmony, they're the fundamental principles. Musica Universalis, it's woven through history. Plato, Kepler, they all wrestled with it. The core idea is that beauty, aesthetic beauty, it's rooted in simple, elegant math, ratios.
And what's really mind-bending is how this ancient quest has, well, evolved. It's not just about planets orbiting anymore, is it?
Not at all. The search has shifted. It's gone deeper, much more fundamental. We're looking at the universal physical constants now.
Okay, constants, like the speed of light, gravity.
Exactly. Think of them as the score the universe plays from, the fixed rules, immutable.
So our big question for this deep dive is, do these fundamental constants, these crucial numbers, like the speed of light, electron charge, gravity's pull, do they relate to each other? Like, with that same kind of mathematical precision you find in a musical scale? Is there a hidden cosmic scale buried in the physics?
That's precisely the question we're tackling. And it takes us on quite a journey. We'll be touching on modern physics, cosmology, but also music theory, philosophy of science.
Sounds like a fascinating mix. So where do we start? With the constants themselves, the orchestra, so to speak.
Let's do that. Define the instruments. What are fundamental constants? At their heart, their quantities, we believe, are, well, universal, unchanging, across all of space and time. They're the essential numbers baked into our most basic theories. They dictate force strengths, particle masses, the very fabric of spacetime. You need their values to make any real predictions.
Okay, bedrock numbers. And you mentioned before we started, there's a critical distinction here, dimensional versus dimensionless. Why is that so important for finding this cosmic harmony?
Yes, absolutely crucial. Dimensional constants, they're things like the speed of light, c, or the gravitational constant, g. Their actual numerical value. It totally depends on the units we choose. Meters, seconds, kilograms.
You change the units, the number changes, like miles per hour versus kilometers per hour.
Exactly. So you could think of them as maybe the rules of tempo or rhythm for the cosmic music. But the number itself depends on our yardstick. It's contingent on us.
Right. So let's talk examples. The speed of light, c. Everyone knows that one. The ultimate speed limit.
The ultimate speed limit, yeah, about 300 million meters per second. But c is much deeper than just how fast light travels. In Einstein's relativity, it's woven into the geometry of space-time itself. It connects space and time. And of course, there's EHIM c pedals. C is a conversion factor between mass and energy. Shows they're interchangeable, really. Two sides of the same coin.
And didn't we recently change how we define the meter based on C? That sounds like a big deal, philosophically.
It was a huge shift. In 2018, we used to define the meter, the measure C. Now we define the value C as exact, fixed. And the meter's derived from it and the second.
Wow. So the universal constant defines our measurement.
Precisely. In our analogy, the cosmic tempo itself sets the beat, and our measuring sticks just have to align with it. It's a fundamental shift in perspective.
Okay, what about the gravitational constant G? This one's weird, right? It's super weak, but it runs the whole universe on large scales.
It is a bit paradoxical. G sets the strength of gravity. It's incredibly weak between individual particles, but gravity always adds up. It's always attractive, unlike electromagnetism. So over vast distances with immense masses like stars and galaxies, it becomes the dominant force shaping everything. It's also notoriously tricky to measure accurately. We only know it to about 4 significant digits.
So in the orchestra, G is like the deep bass line, the foundation.
That's a great analogy. A persistent underlying drone that shapes the whole structure, the large-scale structure anyway.
Then there's the Planck constant, H, the quantum constant.
Right, H, absolutely fundamental to quantum mechanics. It's this incredibly tiny number that tells us energy isn't smooth. It comes in discrete packets, or quanta. The famous equation E links a quantum's energy, E, to its frequency, and H is the constant factor. It dictates the scale of quantum effects, the very granularity of reality.
So if C is the tempo, maybe H is the fundamental rhythm, the smallest possible beat.
That works. It sets the scale for quantum jumps, the indivisible actions. And like C, H was also used in the 2018 redefinition to define the kilogram. These constants are becoming our new foundation for measurement.
Fascinating. And quickly, the elementary charge, E. The basic unit of electric charge.
Yes, E. The charge on a single electron or proton. It determines the strength of electromagnetic interactions at the most basic level. You could think of it as maybe the timbre or voicing of the electric instruments in an orchestra, how they sound, how they interact.
Okay, let's quickly recap the dimensional players. C, tempo, G, bass line, H, rhythm, E, timbre. These set the stage, the rules. But you said the real search for harmony, for pure relationships, lies elsewhere.
Exactly. It lies with the dimensionless constants. Because these are pure numbers, their values are the same no matter what units you use. Meters, feet, furlongs per fortnight. Doesn't matter.
They're universal ratios.
Universal ratios. Like musical intervals, a perfect fifth is always 3.2, whether you measure frequency in hertz or something else. These dimensionless numbers are the real candidates for the pure tones or perfect intervals in the cosmic score.
And the most famous one has to be the fine structure constant, alpha. I think Feynman called it a magic number.
He did. A magic number that comes to us with no understanding by man. Alpha is roughly 1 divided by 137.036. It essentially measures the strength of electromagnetism, how strongly electrons couple to photons, to light. Its value is incredibly critical. If I gamma were 0, no electromagnetism, no light interacting with matter, no atoms as we know them, no chemistry. If we're much larger, atomic nuclei might become unstable. Life depends crucially on it being just this value.
So it's like the strength of a chord, how consonant the interaction is between key players like electrons and light.
That's a nice way to put it. The consonant strength between fundamental instruments.
Okay, another big one is the proton-to-electron mass ratio, usually called alt or beta. It's a huge number, right? Around 1836.
Yes, it's about 1836.15. This ratio is absolutely vital for chemistry because the proton is so much heavier than the electron. You get atoms with tiny, dense nuclei and large, diffuse electron clouds. That structure is what allows molecules and complex chemistry to happen. If the ratio were closer to 1, atoms would look completely different, and the universe likely wouldn't support complex structures, let alone life.
So it sets the relative weight or importance of the main voices in matter, like a really wide interval in music.
Exactly, like comparing a piccolo to a tuba, maybe. A vast interval that defines the character of the atomic orchestra.
All right, this gives us a much clearer picture of the constants, our cosmic orchestra. Now, let's get to the harmony itself. This takes us back to Pythagoras, doesn't it? The whole idea that music is math.
It really starts there. Before Pythagoras, harmony was, well, subjective, what sounded good. He and his followers had this revolutionary insight that pleasing sounds, consonant sounds, correspond to simple mathematical ratios, old numbers.
The blacksmith story, is that true? He heard hammers hitting an anvil?
That's the legend. Different weighted hammers producing consonant sounds when their weights were in simple ratios. Whether it happened exactly like that, who knows? But he definitely experimented with a monochord, a single string instrument. And he showed that dividing the string using simple integer ratios like 2 to 1, 3 to 2, 4 to 3 produced the most fundamental, pleasing musical intervals.
The octave, 2.1, the perfect fifth, 3.2, the perfect fourth, 4.3. These sound good because of the simple math.
That was the monumental insight. Aesthetic beauty rooted in objective, simple integer ratios. It wasn't just opinion, it was mathematics. It suggested the cosmos itself might be built on similar principles.
And from these simple ratios, you can build a whole system, like the musical scales we use.
Precisely. You can take a starting note and just keep applying one rule, like going up by a perfect fifth, multiplying the frequency by 32, and folding the notes back into the octave. That process generates the familiar 7-note diatonic scale.
So complexity from simplicity, a core rule generating a whole structure.
It's a beautiful example of emergence. A simple generator creating an ordered, complex system.
But it wasn't quite perfect, was it? There was a hiccup, the Pythagorean comma.
Ah, yes, the hidden tension. It turns out if you stack 12 perfect fifths, you go up a long way musically. And if you stack 7 octaves, you also go up a long way. You'd think they should end up on the same note, just many octaves higher.
But they don't.
They don't. They're incredibly close, but not exactly the same. 32 raised to the power of 12 is not quite the same number as 2 raised to the power of 7. That tiny difference is the Pythagorean comma.
And this wasn't just theoretical. It caused actual problems in music.
It did. It meant one interval in the scale would sound noticeably dissonant, out of tune the wolf interval.
Oh.
Musicians had to figure out ways to fudge things to temper the tuning.
And this feels like a lesson. Even elegant systems can have these slight imperfections, these near misses. Does that connect back to physics at all?
I think it does, profoundly. Physics is full of these near misses. Think about the proton and the neutron. They have almost the same mass, but not quite. That tiny difference is crucial for the stability of atoms. Or consider the strengths of the fundamental forces, excluding gravity. Physicists expected them to unify, to become equal at very high energies. In the simplest models, they get very close, but don't quite meet perfectly.
So these physical commas aren't flaws, they're clues.
Exactly. They often point towards deeper physics. Maybe there's another symmetry, like supersymmetry, that explains the discrepancy and reveals an even more elegant underlying harmony. The imperfection guides us.
And just like music developed different tuning systems beyond Pythagoras' just intonation, equal temperament to deal with these issues. Maybe the universe isn't built on one single perfect tuning either.
That's a crucial cautionary tale for the cosmic analogy. There isn't one universally best way to tune an instrument or structure a scale. Different systems have different advantages. This challenges a simplistic idea of cosmic fine-tuning. Maybe our universe isn't the only possible well-tuned one. Maybe there are other ways constants could be set up to allow for complexity. Some call the assumption that our way is the only way carbon chauvinism.
Interesting. But the core Pythagorean idea is simple integer ratios showing up that does seem to echo elsewhere in science, doesn't it?
Oh, absolutely. Look at chemistry. The law of definite proportion says compounds always have the same elements in the same mass ratios. Stoichiometry is all about atoms combining in simple whole number ratios. HURO, CORO. It's like nature's recipes are written using integers.
And quantum mechanics too, right? The name itself, quantum.
Exactly. Properties come in discrete packets, quanta. Think of electron energy levels in an atom. They're determined by an integer, the principal quantum number n. Energy is proportional to Mannix 1n additive. It's not continuous, it's stepped, quantized. The universe seems to have a fundamental graininess built on integers.
So this deep-seated belief, this Pythagorean dream that the universe should be elegant, that its fundamental numbers shouldn't be random, that really drives a lot of modern physics, doesn't it? This search for the cosmic score.
It absolutely does. Even though the standard model works incredibly well just by plugging in the 25 measured dimensionless constants, there's this profound aesthetic dissatisfaction. A belief, almost an article of faith for many physicists, that these numbers must come from somewhere deeper. They shouldn't be arbitrary.
It's a psychological drive, a philosophical one.
Both, I think. A desire for meaning, for elegance in the foundations of reality. Why should the universe operate on random-looking numbers?
So let's look at some attempts to find patterns. Alpha, that 11,137 number, seems to be the main obsession.
It's definitely the poster child for this quest. As Feynman said, it's a magic number, unexplained. Its value dictates so much about chemistry and light.
And didn't Sir Arthur Eddington try to prove it was exactly 137, or rather 1137, back in the day?
He did in the 1920s and 30s. He had these, well, rather numerological arguments based on counting degrees of freedom, trying to force old to be precisely the integer 137. His specific methods didn't hold up. They're largely discredited now.
But the spirit of the search lived on.
Oh, absolutely. The hope that I isn't just some random number, but is mathematically necessary, perhaps linked to geometry or other constants in a simple way, that hope persists.
Are there any, more recent intriguing mathematical coincidences involving alpha, even if they aren't proven theories?
Well, people notice things. For example, there's a formula involving the cosine of 1 alpha, cos-A, which happens to be remarkably close to E1 over Euler's number. Is it meaningful? Probably not. Others have played with pi, suggesting maybe 1i is related to the square root of 137 Giroud's cos-A. Again, these are speculative, they aren't accepted physics. But they show that persistent Pythagorean impulse, trying to find simple, elegant origins for these seemingly arbitrary numbers.
It's like seeing patterns in the static. What about the proton-to-electron mass ratio, that 1836 number? Any funny business there?
That one might be even spookier. Back in 1951, a physicist named Friedrich Lenz pointed out something astonishing. The formula 6 fort. Calculate that out.
6 times pi to the 5th power.
It comes out to 1836.118. And at the time, the experimental value for pi was 136.12 plus or minus 0.05. It was a perfect match within the uncertainty.
Whoa, that's uncanny. Does it still match now that we know much more precisely?
Not perfectly anymore. Today's value for pi is 1836.1526734426. So 6 art is off by a tiny bit now, about 0.0002%. But still, it's astonishingly close.
So the million-dollar question, is that a profound hint about some hidden geometry involving pi? Or is it just one of the craziest coincidences in the history of science?
That's exactly the dilemma. It walks that fine line between, insightful pattern spotting and what skeptics might call numerical alchemy. We just don't know.
Okay, so we've looked for these simple patterns, these Pythagorean ratios and the constants. What's the current verdict? Harmony or something else? Atonality.
Well, the honest answer is, despite a century of looking, we don't have any accepted theory that derives these 25 fundamental dimensionless numbers from first principles or from simple generative rules like stacking fifths. The universe's score, as we currently read it from the standard model, doesn't look like a simple consonant melody. It looks more like, well, maybe a complex, modern, even atonal piece. The relationships are precise, essential, but not obviously built on simple integer ratios.
But maybe the analogy needs adjusting. Maybe the constants aren't the notes.
Exactly. Maybe that's the wrong way to look at it. Perhaps the constants are more like the fundamental rules of harmony and composition themselves, or the specific properties of the instruments. Like INES isn't a note. It's the rule defining how strongly the electron instrument and the photon instrument interact, their consonants. The 19 or so free parameters in the standard model might be the complex rules of orchestration and counterpoint for the cosmic symphony. We just haven't figured out the unifying structure, the composer's grand plan yet.
So while the search for that simple cosmic scale hasn't panned out directly, another kind of harmony has emerged, right? This idea of the fine-tuned universe.
Yes, this is a huge area. It shifts the focus. It's less about whether the numbers themselves look mathematically elegant in isolation, and more about how their specific values, even if they look arbitrary, seem to work together in an incredibly precise way to allow complexity, stars, planets, life to emerge.
The universe seems tuned for life.
It appears that way. If you tweak many of these constants even slightly, the universe would be drastically different and likely sterile. It's like the orchestra is playing a piece that, against all odds, allows an audience to exist and listen. The question becomes, was it composed for an audience, or is it just a lucky coincidence?
Let's get into some examples. Fred Hoyle's prediction about carbon is a classic.
It's a fantastic story. Hoyle was working on how elements are made in stars. He realized that to get the amount of carbon we see in the universe, which is essential for life as we know it, the carbon-12 nucleus needed to have a very specific energy level, a resonance, at about 7.65 MeV. This resonance allows 3 helium nuclei to fuse into carbon much more efficiently. He predicted this specific energy level before it was experimentally confirmed. If that resonance were just slightly different, maybe 1% higher or lower, very little carbon would be made in stars. No carbon, no us.
It's like a fundamental parameter had to be tuned to exactly the right pitch.
Precisely. A critical note in the cosmic score had to be hit just right.
And another famous one is the balance between gravity and electromagnetism. Martin Rees talks about this huge ratio, N-SO. Gravity is incredibly weak compared to electromagnetism.
Mind-bogglingly weak.
Right.
But that weakness is essential. If gravity were significantly stronger relative to electromagnetism, stars would form much smaller, burn much hotter, and live for maybe millions of years instead of billions.
Yeah.
Not nearly enough time for complex life to evolve on any orbiting planets.
And if gravity were weaker,
then stars and galaxies might not even condense and form in the first place. The universe would just be diffused gas. So the ability for stars, these long-lived nuclear furnaces that create heavy elements, to even exist depends on this enormous ratio being in a surprisingly narrow life-permitting range.
Wow. Okay, but the most extreme example, the one that really breaks people's brains, is the cosmological constant lambda.
Lambda. The energy density of empty space, driving the accelerated expansion of the universe. Our best theories, quantum field theories, predict a value for this vacuum energy that is stupendously large.
How large?
About 122 orders of magnitude. That's a 1 followed by 122 zeros larger than the value we actually observe. This is often called the worst prediction in the history of physics.
And if it were that large, or even just a bit larger than observed?
If it were even slightly larger than its tiny observed value, its repulsive force would have overwhelmed gravity very early on. It would have ripped space apart so fast that galaxies, stars, planets, none of them could have ever formed.
So the actual value is tuned down by an incredible factor. It's like balancing a pencil on its tip.
But balancing it to an accuracy of 1 part in 10 Babel, it's the most exquisite fine-tuning problem we know of. Why is empty space so, well, empty of energy compared to what theory expects?
So how do we explain this apparent harmony, this fine-tuning across multiple constants? You mentioned 3 main ideas physicists kick around. What's the first one?
The first is the anthropic principle. In its simplest form, the weak anthropic principle, WAP, is just a selection effect. It says, well, of course we observe the universe to have constants compatible with life, because if they weren't, we wouldn't be here to observe them.
It sounds a bit tautological, like we're here because we're here.
The WAP is basically that, yes. It's scientifically sound, but perhaps unsatisfying. There's also a strong anthropic principle, SAP, which controversially suggests the universe must have properties that allow life to develop within it at some stage. That sounds more like design or purpose.
Okay, so WP is observation, SAP is maybe philosophy. What's the second big explanation? The multiverse.
This is probably the most popular naturalistic explanation currently among many theoretical physicists. The idea is that our universe isn't the only one. There's a vast, perhaps infinite multiverse of other universes. And in each of these universes, the fundamental constants might take on different random values. If there are enough universes in theories like eternal inflation or string theory's landscape of tenori geos possible vacua suggest there could be, then just by sheer chance, some tiny fraction of them will happen to have the right combination of constants for stars, chemistry, and life.
So we just won the cosmic lottery. Our existence is just survivor bias on a cosmic scale.
Essentially, yes. Like infinite monkeys typing Shakespeare, eventually one produces Hamlet. We find ourselves in a Hamlet-producing universe simply because we couldn't exist in the gibberish ones.
It explains the tuning without needing a tuner, just infinite chances. What's the third possibility?
The third hope is that the fine-tuning is actually an illusion of our incomplete knowledge. Maybe there's a deeper physical law, a final theory of everything that determines the values of all these constants uniquely. In this view, the constants aren't tuned at all. They have the values they do because they're the only mathematically consistent values allowed by the ultimate laws of physics. There's only one way the universe could be.
So this would restore that Pythagorean dream of a universe dictated by unique, elegant mathematical necessity.
Exactly. It would mean the score is fixed, inevitable, not just a lucky break or a selection effect.
But surely this fine-tuning argument has critics. It sounds compelling, but what are the counter-arguments?
Oh, certainly. One is the puddle analogy from Douglas Adams. A puddle wakes up and thinks, wow, this hole fits me perfectly. It must have been made for me. It doesn't realize it adapted to the hole. Maybe life adapted to the constants, not the other way around.
The survivor bias point again?
Right. Another issue with probability. How do you calculate the odds when you only have one universe to observe? We don't know the space of possible constants or the probability distribution across it. And then there's that carbon chauvinism argument. Are we wrongly assuming that only our kind of carbon-based life is possible? Maybe wildly different universes could host wildly different forms of complexity or consciousness.
It's slippery territory. But this whole discussion, this search for cosmic harmony, it all stems from something deep in science, doesn't it? This belief in mathematical beauty as a guide.
Absolutely. It's not just about fitting data. It's about seeking elegance, simplicity, symmetry. This aesthetic drive has been incredibly powerful in theoretical physics. Paul Dirac is a prime example.
He was the one who prioritized beauty over even experimental results.
He famously said that it is more important to have beauty in one's equations than to have them fit experiment. That sounds crazy, but his deep conviction in mathematical beauty led him to predict the existence of antimatter purely from the symmetries in his equation for the electron. Experiment later proved him right.
That's incredible. A stunning vindication for beauty as a guide to truth.
It really is. And physicists today still rely heavily on this aesthetic sense. Nobel laureate Frank Wilczek talks about what constitutes this beauty in physics.
Yeah.
Two key concepts stand out, linking back nicely to our music analogy.
Okay, what's the first one? Symmetry.
Symmetry. In physics, this means change without change. A system or law has symmetry if it stays the same under some transformation like rotation or moving forward in time. These symmetries aren't just pretty. They are deeply connected to fundamental conservation laws. Time translation symmetry leads to conservation of energy, for example. The search for deeper hidden symmetries has been a primary engine driving unification in physics.
And the second principle Wilczek mentions, exuberance.
Yes, exuberance or productivity. This is the idea that simple, compact starting points, a few elegant equations or principles, can generate a vast, rich tapestry of consequences and phenomena. Think of Maxwell's equations for electromagnetism. Just 4 short equations describe everything about electricity, magnetism, and light, and even predicted things like radio waves. That's exuberance, getting a huge amount of output from a minimal, elegant input.
So connecting back to music, A simple theme input is developed through rules of harmony and counterpoints, symmetric rules, to create a complex, rich symphony, exuberant output. We want the universe's laws and constants to have that same beautiful generative quality.
That's the aesthetic ideal, yes.
Yeah.
That desire for elegant generation is at the heart of the search for a theory of everything, and it echoes Pythagoras.
Which brings us back to this fundamental mystery. Why does mathematics work so well? Eugene Wigner called it the unreasonable effectiveness of mathematics in describing the natural world.
It truly is unreasonable when you think about it. Why should abstract concepts invented by the human mind correspond so perfectly to the workings of the physical universe? There's no logical reason it had to be that way.
Is it evolution? Our brains evolved to recognize patterns, and math is the ultimate pattern language.
That's one line of thought. Finding predictive patterns, whether in the seasons or predator movements or musical harmony or physical laws, is advantageous for survival. So maybe our brains evolved to find pleasure in the kind of elegant predictive patterns that mathematics provides.
And amazingly, brain scans actually show a connection. Mathematical beauty lights up the same areas as art or music.
Yes, studies have shown that contemplating beautiful mathematical formulas activates the same part of the emotional brain, the medial orbitofrontal cortex, as experiencing beautiful music or visual art. There seems to be a shared neural basis for our aesthetic appreciation, whether sensory or abstract.
Which leads us to perhaps the most radical idea of all, John Archibald Wheeler's concept, it from bit.
Wheeler proposed this provocative idea that the physical world, every it, every particle, every field, ultimately derives its existence from information-theoretic foundations, from the answers to yes or no questions, from bits. In this view, information isn't just how we describe reality. Information is the fundamental reality. The universe isn't just like a computation. It is a computation.
So the constants aren't just numbers describing the simulation. They are the core algorithms, the music and the instrument, the score and the performance. They become inseparable.
That's the ultimate implication. The universe isn't like a symphony. It's a symphony made of pure mathematical or informational relationships. The constants are the fundamental ratios. It from bit. What a mind-bending thought to end on.
Wow, what a journey this deep dive has been. We started asking if the universe's constants follow a simple musical scale, like Pythagoras might have hoped.
And the answer, well, it's not a simple yes or no, is it? That direct cosmic scale built on simple generating ratios, like stacking musical fifths, doesn't seem to match the complex set of constants we actually observe.
But the spirit of the musical analogy, the search for harmony, for precise mathematical relationships, for dimensionless ratios that define structure that resonates incredibly deeply through physics.
Absolutely. And the fine-tuning evidence strongly suggests the universe is consonant in a crucial way. Its parameters work together with extraordinary precision to allow complexity in life. It avoids the dissonance of a sterile void.
Which leaves us with those big questions. Is this consonance the result of a deeper, inevitable law we haven't found yet? Is it just one lucky outcome in a vast multiverse of cosmic noise? Or is it simply that we could only exist in a universe tuned this way?
That question, the origin of the constants and their apparent fine-tuning, remains one of the biggest unsolved mysteries. The final movement of the symphony hasn't been written, or perhaps we haven't learned how to read it yet.
But the quest definitely continues. That ancient Pythagorean dream that the universe is built on number and harmony, it's very much alive. It's just transformed into the search for the ultimate laws of physics, driven by that same belief in mathematical beauty and elegance.
It's a powerful motivator at the frontiers of science.
So here's a final thought for you to take away. If Wheeler was right, if the universe really is fundamentally mathematics, fundamentally information, and if our brains evolved to find beauty and meaning in precisely these kinds of mathematical patterns, what does that imply about reality and about our own place within this perhaps unfinished cosmic symphony? What kind of music does a universe made of pure information actually create?